Welcome to day 17 of the EPICS training lecture series. My name is Marty Smith. I work in the APS controls group, and today I'll be discussing some basics about StreamDevice programming for EPICS. So I'll start by giving you an introduction to StreamDevice, how to make your EPICS records use the StreamDevice support, and I'll talk about protocol files and the protocols within those files that are used to talk to the various devices. We'll take I'll show you how to add the device support into an already existing EPICS application. We're not going to get into how do you get all that set up. And then we'll take a short break, and those who are sticking around for the lab, you can actually talk to a network-attached device. So basically, EPICS StreamDevice is a support for a byte stream-based communications to these types of devices. Byte stream, by byte stream I mean ASCII string-based communications, so such as RS-232, GPIB, TCP/IP, and so forth. So you can talk to any of these types of devices using StreamDevice. So it's a basic command and reply response, although you can accept unsolicited messages. Typical commands would look like these. You might notice the first one is basically a GPIB command to get the ID of the device. Also in your protocols, you can include the non-printable characters in your output and your input. The command and reply parsing is configured by protocols and formatted by the interpretation of the format is handled by format converters in StreamDevice. Now you can write your own, but so far I haven't had to do that. So these format converters are similar to the C, printf, and scanf functions. So StreamDevice provides an interface to ASIN device driver, and more specifically to ASIN octet, which handles all of the communications between the device and your EPICS database by exchanging the strings to and from the device. StreamDevice isn't a programming language. You don't have to compile it. So being that it isn't a programming language, there's no looping, no conditionals. It just executes the protocol from the start to the finish. And there are some rudimentary exception handlers that you can use. I won't get into all of those today. So how do we get this to work with an EPICS database? So we have a simple command here. Here's a good example of a command and response from a device that I talk to now. So I send it a Q command, and what I get back is all this data. So your protocol is responsible for taking that string data and parsing it in order to put it into your EPICS database records. And you may only have one stream supported record just to send the Q command. The rest may not even be, they might be soft device type or a soft channel or something like that, where you just parse that string and put it into that record. So you don't have to use StreamDevice for every single record. So here's a good example. So the top record there is the query, and I got that at a 10-second scan rate. So what that will do is it forward links to the next record. So the next record here is actually what does the StreamDevice, talks to the device itself. So the D type has to be stream in that record. And then your input and output fields specify the protocol file name, which is shown here, the protocol entry, which I like to refer to as a function, and you'll see later it looks similar to functions written in C. And this particular one accepts a single argument of $$P, $R, which just happens in this case to be the PV name prefix. So you also have to give it the ASIN port and an address. Now the address can be anything you want, any number. Typically for serial type devices, for most devices it's actually 0. So, and you can have up to 9 arguments in your function call. So I like to call it, although they call them protocols. So for the records there where the D type is not set to stream, like I said before, you can use those. And so the first one, for example, would get the serial number. So in the protocol, you would have an in command, and you would format that as a number and send it to this record. So here's an example of the protocol file, just an excerpt from it that I use for that particular device where I showed all the data coming back. So you say the function or protocol name is called query, and I have an out with a Q. That's it. That's all I need to send. Except that you have to send some kind of terminating character, usually a new line or a carriage return. So the in command, you can see that I'm expecting a :SN equals to be the first thing that comes back in. And then in the parentheses there would be the PV name, and the $1 is the argument that you passed in. In the previous example, that was the PV prefix. So you'll note here that I used the field width to guard against buffer overruns. And so it's going to read 39 characters up to the first comma. All of the commands that come back are comma separated. So we have to include these commas in here because the StreamDevice is expecting what comes back to match what's in your protocol. Okay, so a protocol file is just a plain ASCII text file. Like I said before, you don't need to compile it. It's just read by the IOC at boot time. So each entry in it, you can have a single read, you can have a single write, you can do multiple read and writes in the same protocol. And you can have just one record or many records. It doesn't matter. It's just how does the device send back the information. If it sends back one thing, then you'll have one record. If it sends back a whole bunch, then you'll list a bunch of records. So output records can be initialized from the instrument at IOC startup. So, for example, if you have an on-off button, when you start your IOC, if the device is on, you may want it to show that the device is on. So the only caveat to that is that the instrument has to be powered up and able to communicate when the IOC boots. You would do this by using one of the one of these handlers that it would be the @init handler, which I'll show you in a minute, that would actually initialize that record. So each of the protocols in a protocol file is for one particular device. Well, each protocol file would be for one device. So typically, I name my protocol file something similar to what the device is called. The protocols are defined for each function of the device. So each one of those little protocols or each function would be a single function of the device. In your protocol file, all the lines beginning with a hashtag up to the end of the line are comments. It's kind of typical. A protocol consists of a name followed by the curly braces, like you see here. So it does look similar to a C function. The protocol entries contain statements that will produce output and provide some kind of input parsing if necessary. So this particular one will just send out $1, whatever you passed in as the first argument. In this case, it would have to be the command that you would send to the device to get the output. And it would send back, in this case, a string that would represent a floating point number. So by default, either the val or the rval field is used as the data source or the destination. It just depends on what kind of record you're using. You can refer to any field in the record, or even in a record, like I said, that doesn't use stream. They have C-style escape sequences that you can use, as shown here. You can reload a protocol or reload all the protocols without rebooting the IOC. This is handy when it comes time to when you're writing the protocol file and you need to do some debugging, and it'll be obvious to you because it will print messages like, oh, this PV can't get, this data doesn't match what you're expecting or something like that. And so then you would modify your file, modify your protocol, and then you could use the stream reload for a particular record name, or stream reload with no record name will reload all the protocols for all the records. So then you don't have to, like I said, you don't have to recompile or reboot all the time. You could just reload your protocol file. So you're going to have terminators for all of your string communications. This depends on what the device uses. Some devices use 2 terminators, some use 1. In this case, if you got a carriage return and line feed, then you'd want to specify as the in terminator the line feed character, and you just ignore the carriage return. So in the protocol file, it would look like this. However, I use the asyn terminators, the octet set output and set input end of strings in the boot file. It's just easier to manage that way, and it's not really, the terminators are not really part of the protocol really, but you can put them either way. Okay, so this is an example of the initial readback when the ILC boots. So you can set your at-init exception handler. You set it up like this, and you see this is the set function, and there's a get function. So typically your exception handler for at-init would look exactly like what you have in your get function. You can have it on one line, you can put it on multiple lines like this, your choice. So the set function would just output this and give you some floating point number that you're going to send out. So how do you add StreamDevice to already existing Epic's application? Well, you make changes to your configure release file as shown here. So you got to add the entry for the streams and for asyn, and then you modify your application source make file by adding the DVDs that you need. You need to have asyn and asyn IP port in this case because we're going to be communicating with a network attached device. And you probably use that for serial too. Doesn't really matter, I think. And then you have to include the stream DVD and of course the 2 libraries, asyn and stream. And once you've done that, then you can go into your dbmake file and add entries for the database. And then on the next line there, you can see the actual protocol file, which I tend to keep in my application DB directory. And then the DB installs will install it in the top directory of your application, in the top DB. And I just load asyn record because it's easy for if you want to manually send a command to the device using the asyn octet interface, then you can send that command and you can look at the response, and it's easier to write the protocol that way. So you got to store the protocol file in one of the directories in the stream protocol path, which will be loaded in the boot file. So you can see you modify your startup script, you put the stream protocol path in. In this case, I have the current directory and the top DB directory. Then you would add your IP port configure for asyn, give it the destination address and the port, any other parameters that you might need. And then again, this is where I set my input and output end of strings, and load your databases. And that's pretty much it there. So the port, the port here will be the same as what you put in. It has to match what you put in for the port of your asyn IP port configure. Okay, so Eric Norum was nice enough at one point in time to write this Python script that will emulate a network attached device. So we're gonna set this up. I'll help you set this up. We'll do it together. But some of the commands that are in there are *IDN, the load question mark. This will return 3 floating point numbers separated by spaces. This one in the database I've already done for you as an example. Volts will return the most recent voltage setting and current, the current readback, plus or minus 11 amps. Then we have on question mark, which will return the current on or off status, and then on will pass it either a 0 or a 1, which will either turn the power supply off or on, and volts, which will set the voltage. We got a plus or minus 10 volt range. So those are the commands, and if we start actually, I believe here on slide 15, we can actually get started putting this in now.